Welcome, students, to our very own Magic Science Academy. I'm so glad you're here. Today's explainer is going to uncover the everyday magic behind two super important physical quantities, density and speed. So, whether you're brewing up a heavy potion, lifting a magical stone, or watching your favorite anime hero dash across the screen in a flash, these concepts are absolutely at work. We're going to make this fun, simple, and crystal clear. Let's get started.
Here's our lesson plan for today. First, what exactly is density? Then, lab time, measuring density. Next, how temperature changes density. Fourth, the secrets of speed. Fifth, different kinds of speed. And finally, a quick lesson recap.
All right, section 1. What exactly is density?
To really get a feel for density, I want you to picture something in your mind right now. Imagine holding a 1 kilogram block of solid iron in one hand and a 1 kilogram block of wood in the other, okay? Now, they have the exact same mass, 1 kilogram, but look at them. The wood takes up way more space, right? It has a much larger volume. And this is simply because iron has a higher density. So, density is basically how tightly packed the matter is inside an object. It's the mass per unit volume of a substance. And it's exactly how we figure out if something feels heavy or light for its specific size.
Now, if you're only going to write down one thing right now, make it this magic formula. To find the density of absolutely anything, you just take its mass and divide it by its volume. Yep, mass divided by volume. It really is that simple.
So there are two main ways we actually measure and write down our density answers. If we're in the lab measuring a tiny magic crystal, we'll use the CGS system, which stands for grams per cubic centimeter. But if we're measuring something huge, like, say, a giant boulder, we'll use the Standard International Unit, or SI unit for short, and that one is kilograms per cubic meter.
Let's practice our new formula together, shall we? Imagine we find a special Academy rock. We drop it on the scale and find out it has a mass of exactly 60 grams. Then we measure its size and find it has a volume of 20 cubic centimeters. So what do? We take our mass, 60, and divide it by our volume, 20. And well, 60 divided by 20 gives us exactly 3 grams per cubic centimeter. Look at that, you just calculated density.
Moving right along to section 2, lab time, measuring density. Let's see how this actually works in a real-world experiment. Welcome to the lab. Now, if you have a perfectly square block, finding its volume is super easy. Just use a ruler. But what if you have an irregular solid, like a jagged, bumpy stone? You definitely can't use a ruler for that. So instead, we use water. Here's how it works. Step 1. Measure the solid's mass on a balance scale. Step 2. Pour some water into a tall glass called a measuring cylinder and note the exact water level. Step 3. Gently lower the stone into the water on a string. You'll see the water level rise. That exact amount the water rises, that's the volume of your stone. Finally, step 4. Just divide your mass by this new volume and boom, you have your density. But wait, what if we're in potions class and we need to find the density of a liquid? We obviously can't just pour a liquid directly onto a balance scale. Instead, we use a clever little tool called the density bottle. And this bottle holds exactly 100 milliliters. So first, we weigh the bottle when it's completely empty. Next, we fill it all the way to the brim with our mystery liquid and weigh it again. To find the mass of just the liquid inside, we simply subtract the weight of the empty bottle. Easy, right? Once we have the mass of the liquid, we divide it by the bottle's known volume, which, remember, is 100 milliliters. And there we go, we found our liquid's density.
Which brings us to section 3, how temperature changes density.
We really have to be careful in the lab, though. What if our potions room gets a little too hot? This is actually a really fascinating puzzle. Does heating something up magically change how packed together its particles are? Think about a pot of water boiling on a hot stove. What is actually happening to the density of that water as it gets hotter and hotter?
Well, here is the crucial point. When forms of matter are heated, they expand. They take up more space. Now, for solid rocks, this expansion is so tiny we basically just ignore it. But for liquids and gases, they expand a lot when heated. Their mass, like the actual amount of stuff inside them, stays exactly the same, but their volume gets way bigger. And if we look back at our math formula, if the volume gets bigger while the mass stays the same, the overall density decreases. This is exactly why hot air is less dense than cold air, and it's the exact reason why hot air balloons can float up into the sky.
All right, section 4, the secrets of speed.
Excellent work so far, class. Now that we've mastered the heavy stuff, let's dash right into the second half of our explainer. Speed is all about motion.
Simply put, it's the distance covered by an object in a specific amount of time. Whether it's a student running down the hallway because they're super late for class, or an anime hero dashing across the screen in the blink of an eye, speed just tells us how fast they're changing their position from point A to point B. And you guessed it, just like density, speed has its very own magic formula. To find out how fast something is going, you just take the total distance it traveled and divide it by the time it took to get there. Yep, speed equals distance divided by time. Now, when you look at the speedometer in a car, you usually see kilometers per hour, right? And that's exactly what we use for large, everyday distances. But in physics and science class, our gold standard, the Standard International, or SI unit, is meters per second. This basically just tells us how many meters an object moves every single second. Moving on to Section 5, different kinds of speed.
You know, not all speed is created equal. Sometimes things move perfectly steady, and sometimes they really don't. Imagine a superhero flying smoothly through the clouds at the exact same pace, without ever slowing down or speeding up. That's what we call uniform speed, covering equal distances in equal time intervals. But now, imagine a car driving through a busy city. It stops at red lights, speeds up on empty streets, and slows way down for heavy traffic. That is non-uniform speed, covering unequal distances in those same time intervals. Because city traffic speeds you up and slows you down constantly, it's kind of impossible to pick just one speed for your whole trip, right? So instead, we calculate your average speed. To do this, we just ignore all those little stops and starts. We just take the absolute total distance you traveled and divide it by the total time the entire trip took.
Let's test this out with a pretty fun example. Imagine a little cockroach scurrying across the floor. It covers a distance of 30 meters, and it takes 1.5 minutes to do it. First things first, we need our time in seconds. 1.5 minutes, well, that's 90 seconds. So, we take our total distance of 30 meters, divided by our total time of 90 seconds. 30 divided by 90 gives the cockroach an average speed of 0.33 meters per second. Honestly, pretty fast for a little bug.
And finally, Section 6, quick lesson recap.
Fantastic job today, class. You all did incredibly well. Let's quickly review the core secrets we unlocked in today's explainer. Make sure you memorize these 5 key takeaways. Remember that density is mass divided by volume, and speed is distance divided by time. Don't forget that heating up liquids and gases makes them expand, which actually lowers their density. And finally, always remember your official SI units, kilograms per cubic meter for density and meters per second for speed.
Okay, you've completely mastered the formulas, but I want to leave you with a massive real-world mystery to ponder after this explainer wraps up. Think about what we just learned regarding temperature. If the Earth gets hotter and the oceans heat up, what does that thermal expansion do to the water's density? And if the ocean water expands to take up more volume, what exactly happens to the world map and our sea levels? Think about it and keep exploring the magic of science.